So from the homework that I graded over the weekend, there was a pattern that stood out. Which, this is a pretty small class, but something gets done by more than 1 or 2 students, then something I would bring up. That you need to pay attention to what our boundary conditions are given. In particular, there's a lesson 6, problem 3. That's been a handful of you. Again, and actually, not everybody's turned that homework in. It's like there's a limit to what I can say now, but I think it's the majority of the ones that I graded were applying a different boundary condition to what was written in the problem. And which boundary condition was used in its place varied from student to student. But the point is it didn't match what was actually given. For example, whatever boundary condition applies to u versus u dx, right? That's a whole other boundary condition because when it's applied to u, that's often that indicates sines. Ux that can often indicate cosines, at least when based on what's happening on the left boundary. Or one may have been in some cases with a tendency to fall back on prior examples, assuming that it was just that example all over again. I don't know, but the examples that I give, what I take a lot of time to do is describe, okay, here are the steps we follow. The particulars of a problem may be different, but whatever those particulars are, these are steps you take on a conceptual level, and so things may turn out different in the details, but the general idea is the same. Which reminds me, another setting in which this comes up, and I'm being proactive about this. I give practice tests because I don't want there to be surprises as to what's on the real test in terms of types of problems, types of things that you need to know how to do. But sometimes students take that too far, and it's happened to such a degree that sometimes I consider not continuing this practice. That is, whatever problem is given on the practice test, then the problem of the same type comes up in the real test, but again, the particulars are different. For example, different boundary conditions. And a student will just carry out whatever problems on the practice test, ignoring the actual particulars. Don't do that. The whole point is to be able to adapt to whatever information is given. Okay. I'm going to pull up this particular problem where this popped up. Okay. Lesson 6. Okay. So unshare and reshare. Okay, so we look at the boundary conditions for this problem. So we have u dx at x equals 0, must be equal to 0. And then we have this condition using both u and u dx. Now, this problem so all you're supposed to do, you don't have to solve this problem, but rather transform it into one that has homogeneous boundary conditions. Now, this is somewhat similar to one of the examples that are in the notes. It was the second example that's in the notes that had the same boundary condition on the right side, but not the left. Because in the example, it was u of 0t equals 0, whereas here's du dx. So now if I go to the, let's see if you have these open here, the notes. Here it is. Okay. So here's that example that is somewhat resembles, at least at one of the boundaries. So in the example, we have u is equal to g1 of t, whereas in the problem it's du dx. So what that would mean is you would not have g1 of t here. We don't know what goes here yet because we don't know what u is supposed to be equal to. Now there's always different combinations that can come up, and that is why I describe this procedure best as general as possible. So this will cover not every single possibility, but most possibilities that can come up. There's some combination of u and u dx is that equals something. So what you can always do is follow this, which really brings you here, where you have a formula that's been worked out that will give you the functions k1 and k2 that you can substitute in here, and that's your boundary function. So even though here I started with this and then worked everything out from scratch just to show you how it can be worked out, you're looking for a function of this form. And generally, in the general case, you don't know what k1 and k2 are unless there's a type 1 boundary condition at one end or the other. When that happens, you can fill these in immediately. But if your boundary condition depends on just ux, or it's a combination of u and u dx, these are unknown at the beginning, but they're given by this, where g1 and g2 are whatever boundary values are specified in the original boundary conditions. One exception that comes up is if you have a type 3 or Neumann boundary condition at both ends, something like this, then yes, the above procedure cannot apply because you will be dividing by 0 in this fraction. But here I give you an alternative as to how you can figure it out. So you treat it kind of like a type 1 boundary condition, get your boundary function that way, and then take the integral of it, and then you're good to go. Okay, so be sure to not needlessly lose points by accidentally working out a whole other problem. When it comes to boundary conditions, it's extremely important. It affects the form of the entire solution. So be sure to apply to what's actually given there. All right, so any questions regarding transformation of boundary conditions? Okay. All right, now, last time I started talking about the integral transforms, in particular Fourier transforms, so I'm going to continue with that today. Here, today the focus is just on general facts about Fourier transforms, and then on Wednesday we'll get to more about using them to actually solve PDEs. And Wednesday's lesson will be the last one that will be covered on the first test, which is going to be put out next Wednesday, February 23rd. All right. So Fourier series are for representing functions that are periodic. So here we have we assume that f is periodic, and the period is 2L. So for example, this plain old sine and cosine, L would be pi, or periodic with period 2 pi. So a function of period 2L can be represented by this Fourier series. So we have a constant term that would be the, so a0 over 2, the whole fraction, would be equal to the average value of f during its period. And then we have this infinite sum involving cosine and sine terms. Then we have formulas for the coefficients. Because sines and these cosine and sine functions are orthogonal on the interval minus L to L. So we can use that to get these formulas for the coefficients. So computing the AN and BN is called taking the discrete Fourier transform of f of x. So you can think of it as f being represented either in physical space, meaning a function of x. So here we have f described in physical space. Or you can think of f as being described in frequency space, or Fourier space, by the coefficients an and bn. So the Fourier transform takes your function from physical space to frequency space. And then forming the Fourier series takes you back. If you're starting with the coefficients, you carry out this formula, and then you have your function f in physical space again. Yes?
Why does an start at 0 instead of 1 like the bn?
Oh, okay. So why do we have a0?
Yeah, like no, in like the line below it, like it says like n equals 0, 1, 2, and the next line is like n equals 1 and 2.
Oh, because look at where we have a's and b's in this formula. So I have a0, a1, a2, etc. And the b's, we don't have a b0, so bn starts at 1. But this formula applies to all the a's. And actually, that's why the over 2 is in here. So that we can have one formula that covers everything.
So is that a0 over 2 simply the first iteration of what that sum would be if you started with n equals 0?
Okay. So if you start with n equals 0, I have to be careful about this because of this integral formula. Because you could think of it as coefficient times cosine of n pi x over L, where n is 0, because cosine of 0 is 1. And also, it's safe to start the sum at n equals 0 for the b's, because sine of 0 is 0, and a b0 term wouldn't affect anything anyway. The difficulty is, I'm going to write out as I mentioned, these formulas result from the orthogonality of these functions. And one comment I should make about that, So as far as where 1 over L comes from, okay, actually I need copy and paste this. Okay. Now, so this formula applies. You might recognize this from a prior lesson. When repeating eigenfunction expansions, you take the eigenfunction expansion of some function f of x by taking its inner product with some like xn of x, and then you're dividing by the integral of xn squared. So a formula like this previously popped up in lesson 9. And it just turns out that when you work out this integral, the one in the denominator can be worked out, and it's equal to L. Placed the wrong one. Dang it. Sorry, cursor is really not cooperating. So generally, when you're integrating cosine squared over an interval, or cosine squared or sine squared, in general works out to be half the width of the interval you're integrating over, which the width of the interval is 2L, so we get 1/2 out and we get L. But this only applies for n equal 1, 2, and so on. But if I do the same thing, okay, so now I want to integrate the same expression, or evaluate the same expression for a case n equals 0. All right. So in that case, it's just we have our integrand down here is just 1. So the integral in that case turns out to be just the width of the interval, which is 2L. And then cosine of 0, of course, is 1. So that would go away. Okay, also one more. Cosine. And this actually, so this actually turns out to be the average value of f on the interval minus L to L. So what some books do is so these expressions are consistent, except here we have this extra factor of 2. That's why we have a0 over 2 up here. Because what some books do is say, oh, an is defined to be this for n equals 1, 2, etc., and then they put a 1 over 2L for a0. So our textbook has done this in one formula, but put a factor of 2. Any questions about this Fourier series formula? Okay. Now, here we have an infinite sum. If you remember from Cal 3, spent a lot of time investigating whether a given infinite series converged or not. And how do you know if this even converges, or if it does converge, what does it converge to? So what has been established is that where f of x is continuous, this series actually does, this expression, this series does converge to the value of f of x. Now, it might converge to that value rather slowly, but it does converge. But that's where f is continuous. What if it's not? What if there's a jump discontinuity? So in this situation, suppose f is not actually 2L periodic. So the values at f of L and f of minus L disagree. So in that case, what are you going to converge to? The values are different. So it converges to their average. And in general, if in the middle of the interval, f has a jump discontinuity, again, the Fourier series will converge to the average. So this is called the Dirichlet's theorem. So a failure to be 2L periodic, that implies a jump discontinuity at the endpoints of the interval minus L and L. A jump discontinuity at the boundary or at the interior gives the same result. That Fourier series got to converge to something, so it converges to the average. But if it's converging to the average at a jump, but at points very, very close to a jump, as arbitrarily close to a jump, the Fourier series is still converging to the correct value of f. So that leads to a pretty troublesome phenomenon called Gibbs Phenomenon. That if you compute a Fourier series for a function that has a jump discontinuity, but yet for computing purposes, you have to cut it off at some point. So there's going to be oscillations near the discontinuity. And okay, I'm going to take a moment here and see if I can illustrate this for you, since I happen to have MATLAB open. Okay. All right. Suppose we have a Fourier series for f of x equals 1 on the interval 0 to 1. The Fourier sine series has coefficients that you worked out in a prior homework problem. So Bn is equal to 0 if n even, and it's equal to 4 over n times pi if n is odd. So what I'm going to try to do here is compute several terms of the Fourier sine series and plot the result, and let's see what it looks like. All right, so I'm going to find a vector of values, say 1,000 values between 0 and 1. find sequence of odd integers. Okay, so I'll have, I'll try like, let's say 10 terms, or okay, 11 terms. Okay. So here we have the odd integers from 1 up to 21. So now I need to define a Fourier series coefficient. So that'd be 4 over n times pi for these values of n. Then I need to evaluate sine n pi x for these n. Okay. Now, I want to make this whole thing a column vector. So if I do, okay. So my approximation to sine x, not approximation to fx equals 1. I need to evaluate sine n pi x for all these values of n and for all of these x's. Now it happens to be an efficient way to do that in MATLAB where, okay, I need to make x a column vector. So I'm going to transpose it, that's what the apostrophe does. So this expression here, column vector x, row vector n, is called an outer product. And that is very convenient because an outer product takes every possible product of elements of x with elements of n. So all the different n times x and n times pi. So this will give you value of sine n pi x for all the x's and all the n's. So this will give me a matrix. The first column will be sine pi x. Second column, sine 3 pi x, and sine 5 pi x, and so on. But now I want to multiply them by these coefficients and add them all up. The easiest way to do that in MATLAB is a matrix vector multiplication. This matrix times this vector, which I transpose to make it a column vector. So the result of all this should be, if I'm doing it right, I did not plan to do this today, so is a column vector that is the approximation of the function 1 on the intervals 0, 1 using a Fourier sine series. And if I did this right, I'll plot that and see what it looks like. First of all, make sure I don't have any graphics. Windows open. Wow, I did it right. Okay. Okay, I'm gonna make this a little more visible. Okay, and I'm going to superimpose on it of a function that we're approximating, which is 1, using a red line. Okay. Make that bigger also. So here's a function we're trying to approximate in red. Here's our approximation in blue. So, and of course, it doesn't really work very well to approximate a constant function by a bunch of oscillatory trig functions, but it's doing a decent job. And notice that it is really approaching 1, except at the boundary where it's going to be 0, because your Fourier sine series is going to satisfy homogeneous gear-shaped boundary conditions. There'll be 0 on the boundary. So this represents discontinuity, thus the high-frequency oscillations. This is an example of Gibbs phenomenon. Now, both the function we're trying to approximate and the function we're approximating with are periodic. It's just that the series satisfies boundary conditions that function we're approximating does not. So that introduces the same kind of discontinuity, thus these oscillations. Now, if I were to go further, I only use terms up to n equal 21. So if I refine this, take a lot more terms. So odd numbers up to 201. Recompute the Fourier sine series coefficients. Recompute my approximation. Okay, now what I'll do is I'll delete this one. Okay. And I will plot f again. Oh, whoops. I didn't want it to be red. Whoops. Okay. Okay. So now it's doing a better job in the interior, but this discontinuity is a mismatch between the boundary conditions satisfied by a Fourier series and the function approximating one. It's always going to be a problem no matter how many terms you have. So it'll keep converging more effectively to the points in the interior, but no matter where you cut it off, you're going to have these oscillations near the boundaries. So that's Gibbs phenomenon, which is quite a problem for numerical methods especially. It shows the limitations of Fourier series. We work with Fourier series anyway because it's easy to represent derivatives of functions in terms of when they're represented by Fourier series because it's easy to differentiate sine and cosine. But there's a trade-off. Now we have this problem. I'll post the MATLAB info when I post everything else, in case you're interested. Okay. So in particular for PDEs of constant coefficients, Fourier series are very helpful for getting a solution formula for a PDE. Now this ODE, you see come up often, like for solving an equation like a heat equation using separation of variables. And if you're on the interval 0 to L, then the solutions of this are combinations of cosine n pi x over L and sine n pi x over L. So we've seen examples of that already. Now, what combination of these depends on the boundary conditions. So for example, this type 1 is going to be sines, this type 3 is going to be cosines. If there's a mix of boundary conditions, it could be, it depends on, it could be some combination of these. Now, this is something that comes up in one of the homework problems. The discrete frequency spectrum of function f has these coefficients Cn, which is the square of some squares of your Fourier cosine coefficients and Fourier sine coefficients. And the significance of the discrete frequency spectrum is that you can think of f of x as a sum of waves of frequency n. So we index n from sine n pi x over L, or cosine n pi x over L. Then Cn gives the amplitude of that wave. So this can give you an indication of your function's frequency content. So if Cn is 0 for a particular n, then it has no, then f does not include a wave of that frequency. What if Cn are all 0 for n past a certain threshold? Then we can say that f of x is called band limited, that it only consists of waves only coming from a certain narrow range of frequencies. And this is important for the purpose of approximating f of x using its values at selected points. You need to use enough points to cover its bandwidth. range of frequencies for which Cn is non-zero. Now, everything we talked about so far is approximating a function on a bounded interval, minus L to L. But what happens if you let L go to infinity? Then you're covering a whole real number line. And now your Fourier series, instead of being a sum, can be described as a pair of integrals, one for cosine terms and one for sine terms. And here are the formulas for A and B now. I think I'll put this on a new page. Okay. So here we have similar formulas for A and B, but A and B are now dependent on a continuous variable c instead of a discrete index n. And you're integrating from minus infinity to infinity, and you have a scaling factor of 1 over pi now. Now, if f has some symmetry, like if it's an even function, like cosine, or an odd function, like sine, or if it's an even function, it would also be like even powers of x, like x squared, as opposed to odd powers of x, like x cubed. Then, when you get a Fourier sine and cosine transform, if f is an even function, then b of x c would be 0. And then similarly, if f is an odd function, then this part would be 0. And then you just have the Fourier cosine sine transforms that we see before. You can also define a continuous frequency spectrum. So again, you're taking a cosine coefficient squared plus sine coefficient squared, take the square root, and that is your continuous frequency spectrum. Again, now you think of f is a combination of waves of very different frequencies, where frequency is now continuous rather than discrete. Then this quantity again refers to the amplitude of that wave. So if C turns out to be 0 outside of a certain range of frequencies, then again we can say that the function f is band limited. Okay. Now, another way that I can write this representation of f of x, if I take advantage of complex exponentials. So what I'm doing here is so this is what I had before, this first line. But then I have formulas for a of x c and b of x c, and I've substituted those in here. Then I can represent each cosine and sine using this formula in terms of complex exponentials. So that's what I've done here. And then after a bit of algebra and canceling some terms, and then separating into two integrals with exponents much the same except different signs. But then I can also take advantage of the symmetry and get this one integral from minus infinity to infinity in both physical variable y and the frequency variable c. So this is a way of deriving the Fourier transform that I showed last lesson, that f of x is now equal to this. This is actually the formula for the inverse Fourier transform. And then capital F of xc is the Fourier transform. That was defined last lesson. So all I've done is just derive that from the previous formula in terms of sine and cosine coefficients. So how they're related. So here we're going from physical space. Oh, wait. I have a typo here. That should be, I need to have the same physical space variable throughout this integral, so I change this to x. Okay, that's correct. So here we're going from physical space to frequency space, little f of x to capital F of c, to get little f's frequency content. And here going the other way, from frequency space to physical space to obtain the function of x. That's what the inverse transform does. So we're solving a PDE that's defined on the entire real number line minus infinity to infinity. So you have no boundary conditions. That's also called a Cauchy problem. Then this Fourier transform may be useful for that. Whereas if you have a problem with semi-infinite domain, 0 to infinity, therefore you do have a boundary condition at x equals 0, we solved problems like that earlier, then a cosine or sine transform is appropriate depending on what kind of boundary condition it is. Which reminds me, one of the current homework problems I thought was a bit odd. Lesson 10. Okay, this is problem 10.3. Solving this problem using, it says, by means of a sine or cosine transform. Well, based on the boundary condition, which is the appropriate transform to use?
Sine?
No.
Sine?
Cosine. Because of the u dx.
Oh, I thought it was u. Okay.
Yeah, the u dx cosine, u sine. Strangely, there's an answer to the back of the book for this problem. Strangely, they use sine. Not sure why they did. So, because the formula for a transform of the second derivative, uxx, relies on the boundary value. But in this case, the boundary value happens to be 0, which is convenient. So, but here you're given that the u dx is 0 and x equals 0. If you use a sine transform, you need to know what u is at x equals 0, and in this case, you don't. Yeah, so unfortunately, in the book, there are some issues with answers in the back of the book, so you have to be careful about that. My high school calculus teacher told me that the way it answers in the back of the book for a textbook is the author will, so the professor would delegate that to graduate students, so they go out to a bar and work out problems, and that's the answers in the back of the book. So, my own textbook on numerical analysis doesn't have answers in the back of the book for that very reason. But okay. Yeah, I have come to the end of the notes. But I know we have at least one homework question.
Lesson 9, number 5.
9-5. Okay. Oh, what's the question?
So I managed to get like the S of x t, but I didn't know how to like deal with the summation term afterwards, like how to find out the coefficient.
Oh, okay. So in other words, okay, so you got your new problem.
Yeah.
You solved that up to the point of having the infinite series.
Yeah.
Okay.
I didn't know how to find the coefficient of the infinite series.
Okay. So what happens in this case is, okay, your initial condition turns out to be 0.
Yeah.
But because your boundary function will be a function of t, your PDE is not homogeneous. You're going to have, you're going to subtract off its time derivative here. So now, if I'm going to pull up the notes from this lesson. All right, so that would have been a week ago. All right. Okay, so what happens? Okay, so here's where you're solving your ODEs for coefficients of your solution, where these come from your initial data, which you will have in this case, and this comes from the eigenfunction expansion of your boundary function. So, yeah, so this integral is where your coefficients would come from.
So what will we plug in for the f of s function? Would it just be the like the s of t function, or like the derivative of s?
Okay, well, what happens is, so that function you need to compute these first. And what's going to happen is, okay, your boundary function in this case will be a function of t times a function of x. And for a purpose of computing these, at least you can take the t part and factor it out of the integral and just focus on the x part and working these out. And then whatever you get for this is, is what goes in here. That integral is going to be a bit of a pain. Although, I mean, if you want to use a site like Wolfram to get the integral, I don't care. This isn't Cal 2. But, because normally you have, in this problem, you have to do integration by parts. So, yeah, in fact, yeah, definitely use some assistance to get the integral. Yeah.
This is about the notes about the discrete frequency spectrum. That's related to the Pythagorean theorem, right?
Okay. Sort of. Okay. Where this formula comes from is the fact that, okay, you're expressing your function f as this combination of sines and cosines. Okay, this. And what you're interested in are the ones corresponding to a particular n. Okay. I have to be careful about this. I might be off by a scaling factor, but okay. Where this comes from is, whoops. Parcel formula, or I think it's also written as Parsel's relation, and that is that the norm of f, which is defined to be the integral of f of x squared dx, is also equal to the sum squared plus b n squared, where for convenience I've defined b0 to be 0, because that's what it would be anyway. There might be a scaling factor in here, and I'd have to work carefully to derive the whole thing to be sure. So we're taking sum of squares of all the Fourier coefficients. Now, but you want to focus on just the ones of a single frequency. So actually what you can say is this would be the same as that. So a way to think of it is, if you were to remove all of f's content that was not of frequency n, then this would be the magnitude of what's left that is of that frequency. So you can see the Parsel's formula applied to the restriction of f. Oh, did I answer your question? Or?
I think so. By amplitude, do you mean
How do
corresponding function, like the function evaluated at that,
height of a wave?
the height of a wave? Okay.
It just says regular cosine and sine have an amplitude of 1.
Right.
Yeah.
Okay.
Anything further? Well, I sense packing up, but I don't care if all your questions are answered, then it's fine with me.